All right. So I forgot yesterday to record and no one reminded me, so half my fault, half your fault, right? All right, when I do make these recordings, I'm going to post them on YouTube, and also have a page now on our Canvas page that you can click on. There's a little embedded video there. On the top left-hand side of that, there's a little drop-down so you can select any of the videos that are in this playlist. So. All right, let's take a look at the warm-up. Warm-up says find the general solution to this system, and we're given this system. And over here to the right, I've essentially just copied down that list, that process summary that's at the end of the section. We're going to write the augmented matrix. We're going to go to REF form, that echelon form, that row echelon form. And that step will tell us if it's consistent or not. And then if it's consistent, we'll proceed to the reduced row echelon form and try to find that solution. So let's get started here. First, I'm going to write my augmented matrix. I have 1, -3, 5, 0. And 0, 1, 1, 3. So I have my augmented matrix. Then I want to go and put that into row echelon form. Do I need to do any work here? It's already in row echelon form. All right, so it's already in my REF form here. And so I should be able to talk about it being consistent or not. So is this system consistent? I see some nods. How can we tell that it's consistent by looking at it here? Absolutely. So here we have the fact that our right column, that far right column, is not a pivot column. Tells us that it's consistent. So then it is consistent. So there are solutions. We don't know how many, but right now it is consistent. All right, and that's just fancy notation. It has a pivot column in the far right column. All that's really telling us is that it doesn't look like this. Right? And remember, we go back to systems. This is the case that would say 0x1, 0x2, 0x3 equals 1. Right? Well, that can't be true. So that fancy verbiage of it's not a pivot column in the far right column, that's just telling us that we're not in that case. All right, so we know it's consistent. What about the number of solutions? If there are solutions, there could be one, there could be infinitely many. Can we tell that already as well? One solution or infinitely many solutions? Infinitely many. How do we know that there's infinitely many solutions? That's one way, absolutely. That alone can tell us that there's something there. But let's take a couple steps of that. How does that tell us that there's infinitely many solutions?
There's going to be a free variable.
There's going to be a free variable. We have a pivot position here, a pivot position here. We have our two pivot columns, but there is no pivot position in this column. It tells us the variable here, x3, is going to be a free variable. And we can write the other variables in terms of x3. Right, so we have infinitely many solutions because we have one free variable, at least one free variable. And remember, we check that after establishing this consistent. I can have free variables and still have no solutions. So once I establish there are solutions, then I can use the free variables to determine how many. Okay. So that whole discussion is something that you do mentally quickly, right? You do that first step, you say, row echelon form, oh, yep, there are solutions and there's infinitely many. Great, moving on. You don't have to write those steps every time, but it's an important thought process because if there aren't solutions, of course, you don't want to do a bunch of extra work. So now we're going to do that extra work, though. We're going to take this one and put it into reduced row echelon form. So that's what I have. I'm going to start doing my row operations. In this case, I'm going to leave that last row the same. And my goal now is to eliminate this value right here. All right, so that means I'm going to take R1 and replace it, say R1 plus 3 times R3. I'm going to replace the first row with the first row plus 3 times the second row. Right, and I'm doing that specifically to eliminate this value here. So I have 1 plus 3 times 0 is, of course, 1. That stays unchanged. And then I have -3 plus 3 times 1. That gives me 0. 5 plus 3 times 1 is 8. And 0 plus 3 times 3 is 9. Any questions so far? Once again, check my work, because again, I think I've corrected a mistake that I did in my notes here. So, okay. Now I'm in reduced row echelon form. So now I should be able to pull out my solutions. Process of pulling out the solutions here, it's not trivial. It's not as easy as x1 equals 2, x2 equals 4. This is a little more complicated because of the free variable. So the trick to doing that is to go and rewrite that new system, or rewrite that matrix that we have now in terms of the system. So if I take this augmented matrix, I put it back in the system form, I would have x1 plus 8x3 equals 9. And the next one would be x2 plus x3 equals 3. I'm going to take those things and solve for the leading variables. And once again, this is kind of by convention. I'm going to solve it for x1, and I'm going to solve it for x2 here. So here I have x1 equals 9 minus 8x3, and x2 equals 3 minus x3. Now I'm kind of forming my solution here. x1 equals this thing. x2 equals this thing. What does x3 equal? x3. Yep, it's a free variable. It can be whatever it wants to be. It's going to be my parameter in this thing. Remember, my goal is to find values for x1, x2, and x3 that satisfy my system. So a solution would look like 1, 2, 4, or 3, 6, 8, whatever actually works here. In this case, we can find an example of one of them by saying, if I use x3 equals 1, for instance, I would have a solution that looks like 1, 2, 1. And that could be a solution. But this expression accounts for all the possible solutions. And the nice thing about writing it this way is it's easy to find them all. I just pick a value of x3, and everything's already solved in terms of x3. And this is the parametric form of this solution. It's already all solved in terms of the one free variable. So it's a nice way to represent our solution. In fact, if you've had Calc 3 already, you've seen this kind of parametric form before. I could rewrite this, and instead of using x3 as my parameter, I'll use t, for instance. And I could say that this thing looks like 9 minus 8t, 3 minus t, and t. And that would be my solution here. If you haven't had Calc 3, don't worry about that last thing. I'm not going to do a whole lot with this, and your book's not going to either. But if you have had Calc 3, this is the parametric representation of the solution. And from there we can see that it's going to be a line. All right, any questions about the warm-up? Any questions? Is this the answer we got? Anybody else confirm the answer? Did I make any mistakes along the way? No? Okay. All right, so that's the warm-up. That's like a recap of what we've done in the last couple days. Now our plan for today. Are there questions from the homework for 1.2? After that, we're going to get into section 1.3 on vectors. So, questions. Do we have any questions from the homework? Any questions from the homework? Yep. Sure. Number 5. Just the one? Okay. Find the general solution of the system whose augmented matrix is given below. So let me just grab this thing and clip it into here, and then we'll play with it for a little bit. Okay, so I remember looking at this one and saying, ooh, might not have to do any work for this. Maybe I can just find the solution by looking at it. Great, because it's multiple choice. And turns out I can look back at my solutions here, my options, and already pick out which one it's going to be. I already know which one of these it's going to be. I know it's going to be this one. And how do I know that? Just by looking at this right here. Absolutely. I can already tell right away that x3 and x4 are my free variables. I don't have pivot positions in those columns. So right away I know those are my free variables. I also know it's going to be consistent. I have just zeros here, so that's okay. Here I have a 1 and a 0. Is that all right? That equation just tells me that x5 equals 0, so I have that value already. Alright, so I already know which one it is. The only problem is they want to actually have me type in expressions here. So they're not going to let me get away with just using a little bit of logic to pick the right answer. Okay, so all I'm going to do is take this thing because it's already into a pretty nice form here. In fact, it's already into reduced row echelon form because they've established the pivot positions, they've turned them into ones, and they've also gone back up and eliminated, oops, not that one, this one. Oh, they haven't quite. Almost in this thing here. Let's see. Let's do one operation here. To put it in reduced row echelon form, all I'm going to do is use this 1 to eliminate this -2. So if I did that, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 1, 0, 0, 1, 8, -1, 0, 4. And now I'm going to take R1 and add 2 of this row, row 3. So all this stuff is going to stay the same because I'm just adding zeros to it. This one's going to go away. And then I'm going to have 3 plus 2 times 0. So that's going to stay as 3. Now I'm in reduced row echelon form, and I'm just going to write out my equations now. So first line tells me that x1 minus 5x3 is equal to 3. And then I have x2 plus 8x3 minus x4 is equal to 4. And x5 is equal to 0. And I just solve those for the leading terms. So I'll have x1 is equal to 3 plus 5x3. x2 is equal to 4 minus 8x3 plus x4. And x5 is equal to 0. And the other ones are my free variables. So I should be able to just take those values and put them into here. And if you use, I believe, shift and underline that button will give you the subscripts here. I don't know if you need those or not. Did anybody just put an X with a 3 next to it? Did that work? Or everybody use the underscore? Okay. Other questions? All right, once again, I really encourage you to get a good start on those homeworks so you can bring those questions. Some of the true and false can be tricky, even if you get them right. All right, I mean, you try it once, you get it wrong, you have more than one attempt, you go back and get the right answer. If it's a little confusing, just feel free to bring it up and we'll discuss it. All right, so these are our goals for today. This is the stuff we want to learn by the end of today's class here. We want to know what vectors are, because 1.3 is vectors and vector equations. We need to know how to work with vectors. So add them, subtract them, multiply them by numbers. We need to be able to represent all these things graphically. What does it mean to add 2 vectors graphically? We also have a bunch of vector properties we have to go through. And then really a lot of the new stuff, because all this stuff you might have seen in Calc 2. How many people have not had Calculus 2 here? Anybody not have Calculus 2 at Tech? Okay. Have you guys had vectors before anywhere, other courses? Okay, great. We have calculus or vectors in Calculus 2, which is a little unusual, but it just goes over the basic vector stuff. So a lot of this stuff will be review here. And then our last 2 topics are kind of the new important ideas. We're going to have some new vocabulary, span and linear combination. And lastly, we're going to have to work with that stuff and see how it relates back to linear systems. So, what is a vector?
I'm applying for a new villain loan by the name of Vector. Actually, mathematics. Quantity represented an error in both direction and magnitude. Vector! That's me, because I'm committing crimes with both direction and magnitude. Oh yeah!
All right. So what is a vector? A vector, in one sense, is an object with direction and magnitude. All right, so 2 video clips. So far we've established that I'm kind of old because I'm still reliving The Matrix here. That's kind of an older movie. And I have little kids because it's Despicable Me, right? All right. But it's actually kind of useful because that is one interpretation of a vector. It's an object with a direction and a magnitude. It's kind of the physics vector, right? It's that arrow that goes like that. It has a direction and it has a length. But there's also other interpretations of what a vector is. All right, so this vector I could write as the vector 1, 2. That's one notation for a vector. Vectors also have lots of different notations. I'm going to call this vector the vector v. I'm going to annotate that thing with a little arrow over the top of it. Your text will use boldface when you talk about vectors instead of the arrows over the top. I could write that vector like this, 1, 2. I'll call that a column vector because I'm writing it in a column. Okay. I could also write this vector as 1i plus 2j. That's the I, j, and then k notation if we're having 3 dimensions. So I have lots of different notations for this. If you're going to enter in a matrix or a vector into Mathematica, you're going to use curly braces. Now that's all fine for representing this vector, that 2-dimensional vector with the arrow. But if I can also represent them by lists of values, then I should also be able to say a vector that's this one. This is also a vector. I don't know what that vector looks like because it's in 4 space apparently, in 4 dimensions. But it's still a vector because we can also think of a vector as just an ordered list of numbers. An ordered list of numbers. So the order matters. This thing is totally different than 4, 1, 2, 3. Right? The order matters. Another way we can think of a vector is a small matrix. We've talked about matrices as those boxes of numbers. Well, if I have an m by 1 matrix, which look like that, right? It just has 1 column. That's also a vector, a column vector. And last, I can also think about vectors very abstractly as an element of a vector space. And this is one of the most powerful features of linear algebra, something we'll touch on a little bit in this class, but it's really reserved for the 4000 class and other more advanced classes. But it lets us take all the things that you're going to learn in this class, everything you're going to learn about linear algebra in this class, and extend it to other areas, extend it to functions and more general spaces. So we're going to talk a little bit about that as we go. That's what a vector is. Now we want to work with them. All right, so you guys read the section. Hopefully we got through all these kind of basic operations. So take a second and see if you can do these 4 calculations. Once again, this kind of stuff is not a quiz, so feel free to check your work when you're done with your neighbor or ask a question. All right, what do I have for the first one? What vector is this? 4, 3. Okay, because all we did was we took our 1, 2 plus our 3, 1, and when we add vectors, we add them component-wise. We just add their components together. So the first component will be 1 plus 3, which is 4, and the next one will be 2 plus 1, which is 3. All we do is work with these in components. What about the next one? What's u minus v? Negative 2, 1. What's 2 times u? 2, 4. So when we multiply a vector by a scalar, by a number, we just multiply each of the components by that scalar. And then the last one here, what do we have as an answer for the last one? 1, 7? 11, 7. Everybody confirm that? All right, terrific. All right, so the next thing is what do these things look like graphically? If I've graphed my two vectors, I've graphed u. Here is u, over 1 up 2. Here is my v, that's over 3 up 1. Then now I'm going to plot my u plus v. So u plus v would be over 4 up 3. It'd be right about here. This is the vector that's u plus v. Now there's a couple ways we can think about that. The two best ways are to think about it as a parallelogram. If I were to make a little parallelogram like this, then that sum of the vectors would be the diagonal of the parallelogram. Another way to think about it is by putting them tip to tail. If I take u and I slide it over and start it from v, it's going to point me to that spot where u plus v is going to end. And similarly, I could take v, because the order doesn't matter when I add these two things. I put these two tip to tail, and I should get to the right spot if I had drawn them perfectly. Okay. Any questions about the addition? Subtraction is going to be similar. Subtraction will give me 2, 1. It'll give me this vector over here. You can say, well, I don't know what that is graphically. Well, one way to think about this is if u minus v gets me this thing, then negative 2, 1 plus v should get me to u. That makes sense, right? If I kind of add the v to both sides. Well, then I can think of my tip to tail thing. So if I take v and take this one, tip to tail with v, it should look like that. Okay, it didn't slide very well. But the bottom line is when we take the difference of these vectors, it will be a vector that points from one to the other. And here, the order does matter. If we switch the order, we'll change the sign. So in this case, if I take u minus v, this is a vector that points from v to u. If I flip the order, it would point from u to v. All right, so we have that graphical representation for the difference here. And what's the graphical representation for scaling, for multiplying it by 2? What does that mean graphically? Absolutely, I'm changing the length. I'm doubling the length in this case. So if I plot 2, 4, it brings me up to here. Actually, I'm doubling it. So if I took 1/2 u, it would cut it in half. If I took 1/3 u, it would cut it into a third. Right, so I'm just changing the length here. And the last one, 2u plus 3v, this is what we're going to define as a linear combination of the two vectors. We're just adding multiples of the two vectors together. And the idea here, the neat thing to see, is that in some sense we're going to end up at some point. We're going to end up at 11, 7. And this 2 and this 3, one way to think about it is those are almost the directions of how to get to this point in terms of u and v. Right? Go 2 units in the u direction, and then go 3 units in the v direction, and that's how you get to this point. Because when we think about it, if I have these two vectors, oops, I think I erased one of them. These two vectors, I can really take a linear combination of these things. I can add, subtract multiples of these to get really wherever I want to go. Right, if I take a scaling value of v, it could give me all these possibilities. I can get to all those positions by changing the length of v. But I can also add any length of this thing. So if I want to go to here, I just add a certain distance and a certain scaling of u. So this is a certain length of v, this is a certain length of u. I can really get to wherever I want to go to. And we're going to talk more about that in terms of coordinates a little bit later. All right, any questions about these kind of basic calculations? Okay. All right, so next we're going to work with vector equations. We've kind of done a little bit of this. So take a second and see if you can figure out what W is. What do I do next from this stage that I'm at? With all my vectors. What would I do next here? Yep. Subtract this one over here. I'll get 7, 4. Right? Divide it by 6. Or multiply by 1/6, right? Same thing. Looks reasonable. But can we actually do that? Like, how did we go from this step to this step? We subtracted 2, 2 from both sides. But can we do that with vectors? Of course we can. We just did, right? We just did it, no problem. Everything worked out. But the idea is that's not a trivial thing. There's a reason we can do that in real... We've done that before. So if we look at something like this, 2x plus 4 equals 8, an algebra problem, the first thing we do is subtract 4 from both sides. But there's a reason for that. Because we have properties of real numbers. We know that in real numbers, for every number, we'll write it all in fancy math talk here, for every x that's in R, I'm going to kind of go through some of this notation as we go, but this means x belongs to, is the symbol for belongs to, and this is R, the real numbers. For every x in the real numbers, we know there exists some negative x, that x plus negative x gets me to 0. And so I can choose that negative x and add it to both sides, and I can add 0 on one and 0 on the other. So in that case, I could say, because of this property, I know that there exists this thing that's called negative 4, that when I add them together, I get 0. And there's another property of real numbers, that there exists some element 0, that when I add 0 to any number, I just get that number. And there's all these basic properties we just take for granted when we do algebra because we use it so much. But without those properties, we can't do any of the algebra that we know how to do. So the question is, do we have those same properties for vectors? And the answer is we do. So your book will give them to you. These are all the vector properties. And they should look familiar because if you take the little arrow signs over all those letters, if you said they were just real numbers, these are the properties from real numbers. Right? If we have 2 plus 4, it's the same as 4 plus 2. Well, it turns out it's the same for vectors. Right? So all these are the same properties we've worked with before, and it basically just says, yes, we can do algebra with vectors. Hooray! Now I'm going to talk real briefly about how the book is a little bit backwards on this, and they have to be, because what we're going to do is start with the easy stuff about linear algebra, and then later on, if you take more advanced classes, you really get into the detailed abstract stuff. But they're a little bit backwards here. Here they're going to say, okay, we have these vectors, and we can do all this stuff with them. But there's a more general version of linear algebra that says that these aren't the only things that we can call vectors. This isn't the only thing we can call a vector space. We can make anything we want a vector space. So in general, what we do is we choose a bunch of stuff, a bunch of elements that we want to put into our space. And we define what we mean by addition. Right here I've defined addition to be, if I have 1, 2 plus 3, 4, I have defined addition to be 1 plus 3 and 2 plus 4. But there's no reason I couldn't make up a new symbol called addition and say addition is officially this. It is 1 plus 4 and 2 plus 3. And when you add vectors like this, you have to flip the thing here, right? Sure, why not? I can define it however I want. So in general, what we do is we take a bunch of stuff, elements, we define something called addition, we define something called scalar multiplication, and if the elements in those operations satisfy all this stuff, then we call it a vector space. And all the rest of the stuff you're going to learn in this course will apply to that space as well as this normal space that we work with. Okay? That's the real big picture. Is generally you start with the stuff and the operations, and you have to show all this is true for your stuff and your operations, and then you can declare it a vector space. Here we're just going to start and say we're working with our happy favorite vector space. Okay? Now the other thing about this course is for a lot of students it's our first exposure to proof. Yes! You guys had some proof in geometry and some other courses and loved it, right? Because everybody loves to do mathematical proof. So linear algebra is really a great transition course for proofs. There's some kind of logic that you'll start to learn linear algebra that will help you with other proof classes. So I'm going to do a proof of one of these things for real numbers. And we're not going to prove the rest of them. It's not going to be a huge focus of the course, but I want to show you a little bit just the logical structure. So I'm going to prove the first one. The proof one is, if I write it like a proof, says, if I have some u vector, I'm going to prove this thing in 2 dimensions, so I have u1 and u2. And if I have some vector v, also in 2 dimensions, I have to say what all that u1, u2, v1, v2 stuff are. Those are just real numbers for my case here. So if I have this stuff, then I'm going to try to prove that this is true. Okay? All right, everybody's getting loose now. All right, we're going to get into proof mode. It's going to be a doozy here. All right, so all I want to do is start with this side and see if I can get to the other side, essentially. Remember, as you go through a proof, you have to justify each step. Just like I did for that little algebra problem. We said, oh, we subtract 4 from both sides. Can I do that? No, I have to refer back to the properties I actually have. So I'm going to start with u plus v. Well, I can say that u plus v, because here's my u, here's my v. It should be this thing. It's u1, u2, plus v1, v2. And I know that's equal to u1 plus v1 and u2 plus v2. Why do I know that? Well, by the definition of vector addition. That's how we defined addition. But remember, u1 and v1 are just numbers. And I already know a lot of rules about numbers. So if these are just numbers, well, then I can definitely say that v1 plus u1, or u1 plus v1 is equal to v1 plus u1. I know that's true for numbers. I don't know if it's true for vectors yet, but for numbers, I know that's true. So I can do this. Right, because this is a property of the real numbers. Any questions so far? Now I look at this thing and say, well, that's just v1, v2 plus u1, u2. How do I know that? How do I know that this is the same as this? Definition of vector addition. I don't have that many tools here, right? I only have a couple definitions that I know so far. And because I know what u and v are, this is just v plus u. And that's it. That's the proof. Okay? So it's really not too bad. Right? All we're doing is doing the definitions that we have, the only definitions we have, and then we're using properties of real numbers. You can really go back and prove almost every single one of those properties in a very simple case like that. It's just writing out what the definitions are and using our properties of real numbers. Okay? All right, any questions about that proof? The purpose of that proof isn't so much so that now you know how to prove that, because that will be very important. But just to give you that understanding of a logical proof, that we have to justify all these little steps as we go. All right. All right, we made some progress here. Here's where we're at so far. We talked about what vectors are. We know how to add, subtract, scale them. We know how the pictures look for addition, subtraction, and multiplication. We have the vector properties. Now we're going to get into our last 2 topics here, linear combinations and spans. So what are these things? All right, so they're definitions. So we have to define them. Here are the book definitions. If u and v are vectors, then 2u plus 3v is also a vector. And in fact, any number times u plus any other number times v is also a vector. We can add multiples of vectors together, we're going to get vectors. And when we do that, the result is a linear combination. A linear combination of 2 vectors. And we add multiples of vectors together. So this, as a product, is not a linear combination. I'm not even sure what this means. Squared, I don't think we've really defined that, right? Or actually it's not even really defined, but if it were defined, it would not be a linear combination. All right, we're just adding multiples of vectors together. And we get a bunch of weird results. And if we gather up all the results, all the possible linear combinations that we could get with two vectors, the result would be called the span of u and v. So the span is just a set of all linear combinations of u and v. And we're going to talk about the different spans. So these are the definitions. Any questions about the definitions? What do they mean? All right, let's do a little bit of example here. So we're going to work in R2. R2 is just a Cartesian coordinate system here. We can talk about that as a vector space, looking at all the different points in R2. Or all the different vectors to the points. Really the same thing. So if I have u is the vector 1, 2, there's my vector. What is the span of u? Describe it. So think about it for a second. Write something down on paper as your description. And when you're done writing something down, talk to the person next to you, see if they got the same thing. Compare what you got. If you're stuck, maybe think of some examples. Right? Try to write down a couple of the elements in the span, a couple of the vectors that might be. And once again, really talk to the person next to you and see what they got. You can introduce yourself too. What'd you get? Nothing. That's what I got too, actually. We're taking linear combinations of 1, 2. I don't have anything to add it to, so all I can do is multiply this thing by something. So is 2 times 1, 2 in the span? Sure. Is 3 times 1, 2 in the span? Draw a couple of those. All right, so what does the span of this thing look like now? It's going to be a straight line, right? Because all I'm doing is taking multiples of this thing. I don't have anything else to add it to. So elements in the span could be 1, 2, 2, 4. If I multiply by 2, 3, 6. Thank you. Negative 1, negative 2 would be in there, right? Because I can multiply by negative 1. And let me plot some of these. Well, 2, 4 is going to be right here. And 3, 6 will probably be here, right? Negative 1, negative 2 will be down here. And if I choose any multiple, it's going to be that whole line. Okay? So the span of u is going to be this line. Now what about this one? This is a little different here. The span of 2 vectors. So now I can take any linear combination of these 2 vectors. So I'm taking my regular vector here and I'm adding it to it 1, 0. So that's this vector. What's the span of that thing? Can I get to this point? Is this point in the span? Sure, I just add this amount of u and this amount of v. Is this spot over here in the span? Sure, I just take this amount of u and this amount of v. Is there any point in the plane that's not in the span? No. So the span of these two vectors is all of R2. It's all of R2. The whole plane. What if I add another one? What's the span of this thing? I've added something. Is that span going to be bigger? Is there anywhere I can get now that I couldn't get before? So how would I get out of the page? Let's add a dimension. If I added a dimension, I would have 1, 2, and 1. Right? So what's the linear combination of these three things that are going to get me 1, 2, 1? Right? If I'm trying to find that three-dimensional vector, it would look like this thing, right? How am I going to add these things together to get that thing? Not. Right? So I can't leave this space. I'm still stuck in this space. I can't add a dimension here. So it turns out I haven't added. I mean, before I could already get everywhere. Everywhere R2. Every possible number value of this thing I could get to before. So adding this thing doesn't give me anything extra. The span is still R2. Okay? All right, so that's what the definition of span. We're going to talk a lot about spans and linear combinations as we move through. We're going to talk about in a lot of different contexts. So a lot of these things I'm kind of posing as questions we're going to answer more formally later. So right now you can just think of what a span is by definition. All right, so now we have x1, x2, find x1, x2, such that we have the linear combination of u and v is going to give us 3, 4. All right, so I have my vector u, I have my vector v. I'm saying I can take a linear combination of them, but I want to know the specific linear combination that gets me here. It gets me to 3, 4. So that's the question, and now we're going to talk about the solution and why we already know how to do this. Well, let me just write out what the statement says. It says x1 times u, well, u is the vector 1, 2, plus x2 times the other vector, which was 1, 0. I'm trying to figure out when that's equal to 3, 4. Now before I could just actually multiply through and then move stuff around and just solve it, but now I have two variables, so it's a little trickier. But I'm going to follow the same process. I'm going to multiply this one through. I'll get the new vector x1 to x1. That's what it means to multiply by a scalar. This one's going to be x2, 0, because that's what it means to multiply by a scalar. I have a definition for adding two vectors, so I'm going to add those two vectors, and I'll get x1 plus x2. I'll get 2x1. That's still equal to 3, 4. Then the question is, what does it mean for two vectors to be equal? Are these two vectors equal? Why not? How about a different question? For these two vectors to be equal, what does A have to be? 2. Vectors are equal only if their components are equal. So to say these two vectors are equal is the same thing as saying that x1 plus x2 is equal to 3 and 2x1 is equal to 4. Now do I know how to find the x1 and x2 to satisfy this linear system? I do. I just turn it into an augmented matrix. I go through that solution process. So saying, can I find the solution to that vector equation is exactly the same thing as finding the solution to this linear system. It's exactly the same as finding the solution to an augmented matrix. They're all the same thing. They're just coming from different places. Okay, so those questions are the same. In fact, saying, is there a linear combination of u and v that get me to 3, 4, is the same question as saying, is there a solution to this linear system? Those are also the exact same statements. That's what you're going to see in linear algebra, is we're going to have 10 different ways to ask every single question. All right, so now we know a couple of them. So I want to summarize real quick here. There's really no difference between all three of these statements. Can you find a linear combination of u and v to get me to v? Can you find the solution to this linear system? Right? Can you find a solution to this augmented matrix? All those things are the same question, just in different forms. Okay. Any questions so far? All right, that's really all the big ideas from 1.3. Instead of starting 1.4 with my last 3 minutes, I think I'm going to take a little introduction to Mathematica real quick, kind of to show you how I checked all the homework solutions real quick. Everybody got this copy down? Everybody happy? Okay. All right, so I'm going back up to my first problem. All right, so I'm going to open up Mathematica. Remember, Mathematica is a free download. You can go to the MathLab website or the MTU downloads to download Mathematica. I really encourage you to do it. We're going to have some projects with Mathematica in this course, so it's just good to get started using it. All right. Plus, it's just useful to check your work. You can, of course, check your work with calculators. They can do a lot of the operations we're going to do as well. It just, in my mind anyway, it's a lot easier to do much broader things when you're using Mathematica. So, now the first thing I need to know is how to enter in vectors. Vectors are just lists in Mathematica, and lists are just used curly braces. So if I put in that thing, that's the vector 1, 2, 3. And I could just enter it like that, or I could store it to some value and say, v is that vector. There's my vector v. Okay? Now a matrix is just a list of lists. So I could start a list and say my first list is just the first row. So I could do 1, 2, 3, 1, 1, 1, and 2, 3, 4. That list of lists is a matrix. And I could just run it like that and use it like that, or I could store it somewhere to maybe a name like A. So this is the matrix A. Doesn't look like much like a matrix though. If I want to make it look like a matrix, I could use a command called matrix form. And now I have my pretty matrix. Or I could just type in a little shortcut like this and say matrix form as well. There's my pretty matrix. I could also enter in a matrix. But before I do that, if I want to do certain things on this matrix, there's a whole bunch of commands I can do. We actually don't know a whole lot of stuff to do with matrices yet, but we're going to learn a whole bunch. We're going to learn how to find eigenvalues and eigensystems and all kinds of fancy stuff with matrices. Right now, the only thing we're been working with is how to row reduce these things. So if I want to row reduce, I just start typing row, oh, there it is, row reduce. If I want to row reduce A, there it is. If I want to see it in a pretty way, I use my matrix form, and there it is. Okay, so it's a real quick way to take a matrix, get that row reduced form, and now you can talk about the solutions and work with anything else. Okay? All right, so there's that thing. Another way to enter matrices is to put my parentheses like my matrix is going to look like they look up here. And I'll start entering values. So the one we have here was 1. And then to enter the next block over, I'm going to hit Control, comma. And that will tab me over to the next spot. And I had a -3, Control, comma, 5, Control, comma, 0. I want to start a new row. I'm going to hit Control, Enter. And then I have 0. I just use the arrow key to go over now. There's my matrix. Okay, so I can enter them like that as well. And when they're in this form, I could store it to A like this and use it. But I could also use just that as the argument to my command as well. So I could actually just row reduce this thing. And once again, if I want to see the result in pretty form, I can see the result in pretty form. Okay, so this right now is just the basics. Right now, once again, we said we can also do vectors like we did before. I think I had V up here. I could also say U is equal to 2, 3, 0. And I could say, what is 2U plus 3V? Right, and it'll give me that thing as well. Now later we're going to get into matrix equations. We're going to do all kinds of stuff. And of course, Mathematica can do linear solves and all the other things we're going to need. So this is just the very basics of getting started. But it's real nice as you're doing your homework. Have a little Mathematica box open. Do all the stuff by hand. Get your solution. Type your matrix in here and do a row reduce just to verify your solution. And then you can kind of check your work like that. All right, that's all I got for today. Office hours are right now. And for tomorrow, just go through 1.4. We're also going to have a quiz tomorrow. All right, 1.4 is a pretty short section, so we're going to do that section. And we'll have a quiz on sections 1 through 3. And